Hi, my name is Bob Zolo and I'm a product planner with Agilent Technologies. Today I'm going to do a demonstration of the DC power analyzer, that's model number N6705B, with the battery drain analyzer module installed. The device I'm going to be testing with this test setup is a digital camera. Let me tell you a little bit about this digital camera. It runs off two AA batteries, so it's a 3-volt drive. What I've done is I've taken the AA batteries out and instead I put some clip leads in and clipped onto the terminals. What we're going to do for the first part of the demo is we're going to power this camera from the battery drain analyzer module, so that when we take a picture with the camera, we can actually record the current being drawn from the batteries, which is being substituted by the battery drain analyzer. Once we record that current, we're going to take it and we're going to then play it back onto the battery pack, which I've got here, the two AA batteries. We're going to play it back on that battery pack, and we're going to see what happens to the batteries when you take a picture. So that's an overview. Let me just get started. So the first thing that I want to do is I want to set the DC power analyzer up to power up the camera at 3 volts. So I'll go over here to the voltage setting, and I'll enter 3 for 3 volts. And we'll just leave the current settings as they are, which is a maximum of 3 amps. We won't need that much current to power up the camera. So I'll turn the output on. And now, as you can see, we've got 3 volts on the camera, but there's no current flowing because the camera's not turned on. Let me go ahead and turn the camera on. That'll take a moment for the camera to start up. And you can see the startup procedure pulls, looks like an amp at this point in time, and then it's going to drop back down to about 600 milliamps. And I think it's going to settle out at about 200 milliamps or so when the camera boot up process is done. Okay, looks like we're pretty much there. It's about half an amp static current. Now, most of that current actually is being drawn by the backlight on the camera, but we'll see, there it is, down to about 200 milliamps, and that's when the backlight went off. So you can see just the backlight itself was pulling about 300 milliamps, so we're learning a little bit something about how this camera works. Now, the primary tool I'm going to be using for analysis is the software, and that's being shown on this large monitor here. This is the 14585A control and analysis software for the DC power analyzer. And in the mode I have it right now, it's in data logger mode, and it's a grid, so we're going to see volts or amps in this direction and time in this direction, and we're going to set it up to take a picture and capture that waveform. So let me make a few adjustments to the data logger mode. I want to set the duration to be 30 seconds, which is good, so I'm going to take a picture. We're going to record 30 seconds, we take a picture, and we're going to save that to the data log file, which is fine. All I need now is to set up the amps per division, and we've got it set to 500 milliamps per division. Okay, so let me start the data logger, and then I'll take a picture. So here's the data logger started, and now I'll take a picture. Okay, and now let's look and see what happens as we go along. So it's going to take about 30 seconds. We're about 15 seconds into the data log right now. And another 10 seconds or so, the data log will be done, and we'll have a 30-second long trace. And then we can analyze that waveform and see what interesting information we may learn. All right, looks like we're about done. Okay, so the data log is done. Let me first blow this up a little bit to make it a little easier to see. So I'm at 500 milliamps per division. I'll jump it down to 200 milliamps per division. Okay, now we can see something a little more clearly. So let's use the marker, this marker number 1 here, to make some measurements. So before I took the picture, the marker is showing 223 milliamps, and that was the current that the camera was drawing with the backlight turned off, which is the state it was in before I took a picture. Then at this moment, I took the picture, and you can see a pretty high peak current. If I move the marker into the area, the peak current was about 1 amp, 1.08 amps. It did some activity as it took a picture, and then there was some period of time out here when the backlight was on, but nothing was happening. And the current there was about 500 milliamps, and then a few moments later, the backlight turned off, and the current level dropped down to about 220 milliamps. So this was the complete cycle of taking a picture from the backlight off, to taking the picture, to the backlight on, to the backlight off again. And in fact, one of the interesting things you can do with the software is I can use the markers to denote a section of time, which I'm about to do right now, and we'll put the markers over the entire event from start to finish. And we could read off on the screen that that time is about 21 seconds. And this is a nice feature. Here it shows the capacity of the battery that was consumed during that event. So this took about 3.5 milliamp hours of energy out of the battery to take a picture. And that's what's going to limit how many pictures you can take. Each time you take a picture, 3.5 milliamps comes out, so you'll end up consuming the battery at that rate. But what we really want to do is actually measure that from the battery. So the first thing I want to do is I want to save this waveform. So I go File, we want to export the data, and we're going to export channel 3, the current measurement on channel 3. Okay, and we say OK. And let's just leave it on the desktop, and we'll call it camera 1, or ERA 1. And I already have one named that, so I'm just going to overwrite it. Yes, and now it's saving it. Okay, now, so now that we've saved the data, what I want to do now is I want to invert the data in order to play it back as a load on the battery. So think about it. Right now what we're seeing is positive current, that was current flowing out of the power supply into the camera. What I'm going to do now is I'm going to disconnect the camera, and I'm going to plug in the battery in its place. So here's that battery pack, and it's just got a set of clip leads on it that has it clipped on. So we'll leave the battery there. We will connect it up to channel 3. Now, as we discharge that battery, which in fact it's discharging quite a bit, so let me turn the output off so it doesn't do that. When we discharge the battery, we'll have a positive voltage and negative current as the current flows out of the battery into the power supply, whereas the power supply now, the battery drain analyzer, is acting like the camera on the battery. So before it was acting like the battery on the camera, now it's acting like the camera on the battery. So let's get that set up. So the first thing I want to do is set the voltage, change the mode on the instrument. So I go to Settings, and right now it's set up as a 2-quadrant power supply. I want to set it up as an electronic load. So we're going to set it up as a CC load. And that's, I think, all I need to do at this point. So I go back to the meter, and I'll set the load current to 0 amps. And I'll turn the output on. And what we should see is this is the natural voltage on the battery, 2.9 volts, and no current flowing. And if I disconnect the battery, you can see the voltage goes away. And if I connect the battery again, there you can see that's the unloaded battery voltage of 2.9 volts. Okay, now I'm going to go back to the computer software and do what I need to do there. So this waveform you see on the screen right now is positive current flowing from the power supply into the camera. I want to invert it and make it negative current flowing out of the battery back into the power supply. So let me go to the arbitrary waveform generator function and do that. I go to arb, and what I want to do is I want to go to this channel here, channel 3, and I want to make the voltage fixed. I don't care about voltage, I care about current. I'm going to do what's called an arb on channel 3. So let me get this guy, is the one I want to talk to. So the first thing I want to do is I want to build up a sequence. So I say add, and I want to import a file. And the file that I want to import, new, is this camera 1, and I import it. Okay, and there it is, camera 1. And now I want to invert it from positive current to negative current. So I say modify, and there's the positive waveform. And instead I want to mirror it. Now it's negative current. So now instead of being positive, you can see everything's negative, and this will be the load current that we apply to that battery. So we say save the result. And let me rename this so I know what I renamed it, and we'll call it flipped 1. Okay, there we are, flipped. All right, so we've added that in, we say done. So there's that negative current. And the last thing that I want to do is I want to have it go back to 0 amps when we're done so we don't discharge the battery unnecessarily. So I'll add another step, and that step, so that's done. I want to add another step. This time I want to add in a step waveform, and I just want to go to 0 amps on the stepped waveform and say done. And now it'll just drop back down to 0. Okay, so we're all set. We've got the arb set up to apply the current waveform to the battery. We'll go back to the data logger. Let's clear the screen on the data logger. This time we're going to go negative current, so I've got to slide this guy up. And let's just make the data log a little bit longer. We'll make it 45 seconds so that we can see the entire waveform from before. There's 45 seconds. Okay, we are good to go. So I will start the data logger. I'll start the arbitrary waveform generator. And now you can see this, the waveform. Here it is. It was 0. I started the arb. There's the 200 milliamps. In fact, let me bring this up so you can see it a little clearer. There's the camera pulse, the picture being taken, being applied. Here it ends up as the backlight on and nothing happening. And then in a moment, you'll see the backlight turn off and it'll drop back down to that lower current level. And then when we get to the end of the waveform, it goes back down to 0, which was the last thing that I put in. Okay, so let me turn the output off. All right. Oh, we had it set on continuous, so on continuous is going to keep applying those, but I didn't want to do that. That's okay. This is the part that I'm interested in. So sure enough, if I bring the marker over to here, maybe even bring this up a little higher, we can see the negative current that was applied was that same 1 amp of negative current at the peak that we had before. If I put the marker over here, we can see the current is negative about 500 milliamps with the backlight turned on. Get this marker out of the way. If I put the marker over here, you can see the negative 200 milliamps, which is with the backlight turned off, and then at the end it goes down to 0 amps, which is minus 3 microamps, basically 0 amps. And if I use the markers to measure the capacity, as I did before, that was consumed during it, I put the markers across the entire event. The event is that same 22 milliseconds I mentioned before, and there's the minus 3.5 milliamp hours, or that's the current we pulled out of the battery. So effectively what we've done during this demonstration is we've used a record and playback feature where we've recorded the waveform from the real device and then we played it back on the battery in order to test the batteries and see how the battery would react to the camera having a picture taken. Thank you.